26 April 1986. A reminder that power without control can change the world forever. In 1986, one of the greatest disasters in history occurred: Chernobyl. But no, the main problem was not enriched uranium. Many people think wherever there is uranium, it means a nuclear explosion, but that is completely wrong. At Chernobyl, the uranium was only enriched to about 3 to 5%, enough to produce electricity, not an explosion. What actually happened was a fatal mistake: a sudden surge in reactor power, massive steam buildup, and an explosion. Not nuclear, but a physical one. But the real danger began after that. Not fire, not smoke, but something invisible. Radiation. Radioactive materials were released into the air, carried by the wind, spreading thousands of kilometers away. Within just hours, an entire city became uninhabitable. Not because of the explosion, but because of contamination. People had only a few hours to leave their homes, and they never returned. And this is where we understand a crucial truth. The danger is not just in the level of enrichment, but in control, design, and human error. But to truly understand this story, we first need to understand one thing: uranium. The story of radioactive elements is not just a scientific story, it is a global competition between countries and scientists. It all began in Germany in the year 1789. Martin Heinrich Klaproth discovered an element that would later change the world: uranium. He named it after the planet Uranus because it had just been discovered at that time, without knowing the power it held within. Decades later, in Sweden, in 1828, Jöns Jakob Berzelius discovered another element, thorium, and named it after the Norse god of thunder, Thor. But the real turning point happened in France, in 1898. Marie Curie and her husband, Pierre Curie, discovered two remarkable elements: polonium, named after Marie Curie's homeland, Poland, and radium, from the Latin word radius, meaning ray, because of its intense radiation. This was the moment humanity realized that atoms could release energy on their own. 1 year later, in France, in 1899, André-Louis Debierne discovered actinium, a name derived from the Greek word for ray. In 1900, in Germany, Friedrich Ernst Dorn discovered a strange gas, radon, named after radium because it is produced from its decay. In 1917, in Germany and Austria, Otto Hahn and Lisa Meitner discovered protactinium, meaning the parent of actinium, because it transforms into it. In 1939, in France, Marguerite Perret discovered one of the most unstable elements: francium, named after her country. France, an element that exists only for brief moments. And finally, in 1940, in the United States, Dale R. Corson and his team created astatine, a name derived from the Greek word astatos, meaning unstable. And among all these elements, one of them, more than any other, changed the fate of the world: uranium. But here's an important question. If so many radioactive elements exist, why do we mainly use uranium to produce energy? The answer is simple. Not all radioactive elements are the same. Some of them are far too unstable. They decay so quickly that they cannot even be stored, like francium, which exists only for seconds. Others barely exist in nature and must be created in laboratories, like astatine. And some, although radioactive, are not suitable for energy production because their reactions are not controllable, or they do not produce enough energy. But uranium has a unique property. It is not so unstable that it disappears instantly, and not so stable that nothing happens. It sits at a perfect balance, where its reaction can be controlled. And that is exactly what we need to produce electricity. That's why uranium became the most important nuclear fuel in the world. But here's an important question. If uranium is element number 92, what does that number really mean? This number is not just a label, it reveals what is hidden inside the atom. To understand this, we must go inside the atom. Every atom is made of three main particles: protons, neutrons, and electrons. Protons carry a positive charge, and they are located at the center of the atom, inside the nucleus. The number of protons defines the identity of an element, which means if an atom has 92 protons, it is always uranium. But alongside protons, there are neutrons. Neutrons have no charge, yet they play a critical role. They act like a glue, holding the nucleus together, preventing the protons from pushing each other apart. Now, here's the key point. The number of neutrons can change without changing the element itself. And this leads us to an important concept: isotopes. Isotopes are atoms of the same element, with the same number of protons, but different numbers of neutrons, which means they are all uranium, but they behave differently. For example, U-235 and U-238 both have 92 protons, but different numbers of neutrons, and that small difference creates a massive change. Now let's return to that number, 92. It means that inside uranium, there are 92 protons. Protons that repel each other, creating an enormous tension inside the nucleus. And as this number grows, the pressure increases until the atom can no longer hold itself together. But this pressure does not last forever. It only takes one tiny particle, a neutron, to break this fragile balance. And in a single moment, the uranium nucleus splits apart, releasing an enormous amount of energy. But uranium does not exist in this pure form in nature. This element is hidden deep inside rocks known as uranium ore. To use it, these rocks must first be mined. Then, in processing facilities, they are crushed and refined until a material is produced known as yellow cake, a yellow powder that still cannot be used directly. For the next step, this material must be converted into a gas called UF6. And this is where one of the most complex technologies comes in. Centrifuges, machines that spin at incredible speeds to separate different uranium isotopes from one another. But here's an important question. When we say uranium is enriched to 3%, or 20%, or even 90%, what does that really mean? These numbers do not represent the purity of the material. Instead, they show how much of a specific isotope is present, an isotope called U-235. In nature, most uranium is U-238, and only a very small amount, about 0.7%, is U-235. But that tiny fraction is exactly what we need. So in the enrichment process, what we do is increase the amount of U-235. For example, when we say 3%, it means that out of all the uranium, only 3% of it is U-235. This level is enough to produce electricity in power plants. But if this number increases, for example, to 20%, more energy becomes available. And if it reaches around 90%, then everything changes. But what exactly does a centrifuge do? When uranium is converted into UF6 gas, it is fed into a machine called a centrifuge. This machine spins at extremely high speeds, so fast that the tiny difference in mass between isotopes becomes separable. The heavier isotope, U-238, moves toward the outer walls, while the lighter isotope, U-235, remains closer to the center. And this process is repeated again and again until the percentage of U-235 increases. But here's an important point. Inside the centrifuge, uranium exists as a gas, but after this stage, it is converted back into a solid form, usually as metal or nuclear fuel. And contrary to what many people think, uranium does not explode easily, even at very high enrichment levels. To produce an explosion, very specific conditions are required, which do not occur easily in nature or during transport. But that does not mean it is harmless. Uranium is still a radioactive material, and prolonged exposure to it can damage the human body. And if its particles enter the body, they can become dangerous. And in certain situations, if not properly controlled, it can lead to environmental contamination.